Okay, I want to welcome all of you to this PolarConnect event with Operation IceBridge in Antarctica. We're excited today because we have PolarTREC teacher Maggie Kane, who's based in Punta Arenas, Chile, for this operation, and she'll be presenting from there. And we also have researcher and lead scientist John Woods, who is not in Punta Arenas, Chile right now. He is actually in McMurdo, Antarctica, who's going to be helping Maggie along with this presentation. The other researcher, Nathan Kurtz, was unable to join us today. It's November 2nd, 2016, and I'm Janet, and I work with ARCUS, and we'll be hosting this presentation for you today. A few things before I turn it over to Maggie and John. This presentation is using a platform called Adobe Connect, and you should see the slides changing in the center of your screen. There's a chat area. Some of you are already chatting away, but as we go through, we'd like you to introduce yourself, tell us who's in the room with you, and where you are calling in from so we get an idea. The chat area is also a great place for posting your questions, and we will get those relayed to John and Maggie as we go along and have them answered. This event will be archived, and so we will post it on the website and share it with everybody that has registered as well. Like I said, you please go ahead and introduce yourself. I see that's already happening there. There is a list of participants that you can also see who else has joined. So why is Maggie in Chile and working with Operation IceBridge? She's part of a program called PolarTREC, Teachers and Researchers Exploring and Collaborating. It's run by a nonprofit that Judy, who's also online, and I work for. It's called the Arctic Research Consortium of the United States. It's a lot to digest, but basically we're a nonprofit where we we have a program where we place teachers with researchers in the polar region. Sorry about that. And they get to work with scientists and learn what the scientists are doing and bring that back to their classroom, and that's what Maggie's doing with NASA. I mentioned about questions as we go along. The best way to address questions is actually put them in the chat area. So if you're in a big classroom, maybe gather up questions from your students as we go along and post them there, and we'll relay them. And at the end of the presentation, we'll remind you how to ask questions, and if we have time, we'll do live questions from the audience there. So with that, I'm going to turn this over to Maggie to introduce herself and the team. And just a heads up, she's going to probably turn off her webcam in a little bit because of the bandwidth issues, but we'll let her figure that out. So Maggie, it's all up to you.
Awesome. Well, I can't tell you how exciting it is to be here doing this today. I've been thinking about this for a long time and really excited to bring this experience back to friends and family and colleagues and students back in the U.S. So thank you all for taking time to be with us today to learn a little about this project, which is truly an amazing, groundbreaking project of, I think, real significance to our planet. So this isn't really about me as much as I'm a vehicle for the science and the thinking and the questioning that it's all about. As Janet mentioned, Nathan was not able to be here in the last hour, and so I haven't changed the slides to reflect his not being in the room. So anyway, Dr. Nathan Kurtz is amazing, and I get to work with him every day. And he is the project scientist for Operation IceBridge, and pretty much calls the shots on where we're going to go and what we're going to be studying on a daily basis, and keeps track of everything. So he's got a pretty big job. And as you probably know, I'm the PolarTREC teacher, and I teach at Rocky Mountain School of Expeditionary Learning, hey Remzel, in Denver, Colorado. I teach 9th through 12th grade science, and it's a pretty amazing school. And so students here have already been hearing about some of the cool things that we get to do at REMSL. So next slide, please. So a little about me. I'm very fortunate to have gotten to do a lot of really amazing adventures in my life, and this is definitely one of the big ones. I was a PolarTREC teacher 10 years ago in 2006 in Svalbard, which is part of Norway. It's not connected to Norway geographically. It's up much closer to the pole. And if you ever watched or read The Golden Compass, that was supposedly something to do with Svalbard. But there are a lot of polar bears up there. It's a very, very different place being in the high Arctic. And the picture that you see of me in a red coat, that was on Svalbard. So you can see that it's land, but in the Arctic, there's an awful lot of water and ice in the water, and much less land than where we are now studying Antarctica. So it's a very, very different place. So for me, in my interest of all things glacial and ice related and polar related, what a dream it is to get to go down to the other pole. So I am really lucky to be here, and I'm about halfway through my stay and just learning bucketfuls every day. Next slide, please. So this is Nathan, who's not with me today. And I'm going to turn off my little picture. But this is Nathan, and he's been working for a lot of years in the polar regions. He is really interested in sea ice and has taught me a great deal about sea ice and the importance of sea ice. When we think about ice, we may not really even think about it as being different kinds of ice, but there are lots of different kinds of ice, and I'm learning a lot about that right now. And John, I don't know if you want to jump in at all at this point and tell a little about yourself. This would be a good time to do that.
Hey Maggie, this is John Woods. Like you said, I'm down here in McMurdo Station, Antarctica, which is one of 3 U.S. bases, but definitely the largest and sort of the main hub for U.S. science here in Antarctica. And I'm down here right now. I just left Punta Arenas. Unfortunately, Maggie and I crossed paths, but I'm down here right now prepping for next year when we come down here with a different aircraft, the P3 aircraft. And we'll be actually operating out of McMurdo Station, which lets us hit a couple different science targets than you're currently surveying over in Punta Arenas. So I'll be standing by here for questions. Anything you got, Maggie, you can send our way. And we actually also have one of the NASA pilots that'll be operating down here in the room with us. So if there's any pilot questions that come from the audience, we'll be happy to field those from here.
Great. Thank you, John. That's awesome. So yeah, in that last slide with Nathan, it showed him standing by the Greenland ice sheet, because this project, Operation IceBridge, takes place at both poles. We're in the spring season in Antarctica, and so we are studying down here right now. And I think they try and come here when the ice is sort of at its most extent, right before it starts to break away and float off. So it's a strategic time of year for this study here. And they're over Greenland in May, I believe, April, May, and also did a tour over Barrow, Alaska in the summer. So really looking at some of the different parts of the polar regions to study the ice. Next slide, please. So most of you guys know about NASA, and when you think about NASA, you think about going into space and being an astronaut, and all that's really amazing and true. But NASA also studies Earth, because after all, Earth is one of the planets. And so NASA has a pretty big airborne department that is able to study the Earth, as well as the satellites and other instruments from the ground that NASA has to really understand the processes on Earth and how Earth is changing. And so a lot of people don't think about that when they think of NASA, but it's a pretty robust program. Next slide, please. So this image is kind of cool, and it shows some of the different instruments that are airborne or up above us that NASA uses. So there was a satellite called IceSat. It's now known as IceSat-1, that operated for several years and collected some really important information about the ice in the polar regions. But that satellite is no longer functioning, and so a new one is being designed and hopefully will be sent into orbit 2019, it says on here, so that's a couple years away. So in the meantime, in between, and probably overlapping and hopefully continuing for some time, is the airborne mission of Operation IceBridge, which was designed to bridge the gap between the two satellites. And Operation IceBridge uses, as John said, a different airline for different regions. But right now we're using this DC-8 that we're going to see a close-up of in a minute. Hopefully in a few years when IceSat-2 is up and running, we'll have double doses of this great data. So there's a lot that's going around out there to try and figure out what things are happening and changing on Earth. But honestly, the satellites haven't been at it for all that long, maybe about 50 years. So the data is relatively young. And for students of mine at Remslow in 9th and 10th grade, you remember that when we're talking about climate change and climate, we're really talking about 30 years or more is climate, and anything shorter period of time than that is really not considered really climatic shifts yet. So having only 50 years with a satellite is pretty small amount of time, but it's every year increasing more, so that's great news. Next slide, please. So one of the great advantages of flying an aircraft such as the DC-8 over the surface of land or ice is the amount of detail, where we fly very low. We fly 1,500 feet above the ground, which honestly, it feels like I could just reach my arm out the window and touch the ice. It feels that close. Of course it's not, but it feels really close, and the scale is very hard to tell. So I have gotten some questions on pictures that I've posted in my journal about, wait, how big is that? And it's really hard for me even to answer the question. But the detail is terrific because we're flying so low. We have different aircraft in Operation IceBridge, as I've mentioned. And John, maybe you can jump in on other aircraft other than the P3, which is a pretty small craft. That's what you use over Greenland, am I right?
Hey Maggie, yeah, that was talking about the P3?
Yeah.
Yeah, so the P3 is our main workhorse, especially for the Greenland deployments, and that is the plane that we'll be bringing down here to McMurdo next season, and did come here in 2013.
Okay. Yeah, and then the DC-8, as you can see in the picture, is a pretty big plane. It's a lot like a commercial jetliner. In fact, it's we used to fly on DC-8s, DC-10s back in the day. And so it's pretty, regular looking plane. Like you could say, oh yeah, that looks just like a plane I would get on. It was built quite a while ago, and it is a great plane. It's got a lot of fresh parts, a lot of fresh big engines and so forth. Nice big wingspan. It's really stable up there in the air. So it's a great big plane to carry a lot of instruments. And so really, that's one of the coolest things about this operation is the suite of instruments that are assembled on this plane. We have quite a few that are embedded in the belly of the plane, sort of looking out, radars and other instruments that are measuring various things are right on the belly, the bottom of the plane. And then one of them is inside the plane, just sort of bolted to the floor. But there's a lot of instruments in there that are really designed to help us understand about how the climate is changing and how our sea level is doing as far as ice melt adding to ocean levels. So it's got a pretty sophisticated group of instruments inside that are really well designed. Next slide, please. So the picture on the left shows a picture of Antarctica, and it looks funny. The colors look funny, but the colors really represent a elevation, sea level. John, maybe you want to jump in on what the purple there means, but my understanding is that those are pretty low areas. So the one near the bottom, that's the brightest purple, is where we're actually close to where we're flying today. And we're looking at that area with a lot of interest because of the interface between the ocean water below and the ice shelf that is interfaces with the water. So it's actually free from the land at that point. It may be connected back to glaciers, but it is floating on ocean water. And ocean water is inherently warmer than ice because it's water. And so when you have that, that situation, there's potential for a lot of ice melt pretty quickly. So it's a really interesting area to go to. And on the right-hand side of this slide, it mentions the different instruments. And we do have some pretty amazing instruments that are able to measure not only the height of the elevation and surface of the ice, but of snow as well as radar that can penetrate through the ice, showing some banding of seasonal ice and or annual ice, and going all the way down to bedrock. So if you think about the power that that radar must have to penetrate all that ice, because some of this ice is like over a mile thick, 2 miles thick, it's pretty astonishing. And then there are instruments that are, the gravimeter is fascinating. And we heard about this from John when he came to our school a month or so ago. And I've learned a lot about it, or a little bit about it, but it's fascinating. And basically what it's doing is measuring from the plane where it sits, sort of like a, well, it looks sort of like R2-D2 inside the plane, or like an old washing machine or something. And so from that instrument down to the earth, basically through measuring acceleration, we're able to figure out the gravity. So what that tells you is how much mass the rock or ice or water below has, and very subtle differences tell you what it's made of, what the material below you is made of, whether it's rock or water or ice, which gives you then the shape of the bedrock below, which is incredibly difficult to get any way possible that you could imagine, considering it's covered with ice. So it's really, really cool tool. So that's the gravimeter, and we have digital mapping system that's able to show us precisely where we are and give really precise instruments readouts of the what's below us. And John, do you want to jump in at all about any of these instruments?
Yeah, hey, so, you know, it's, you described them really well. I think it's, what's really neat is just the varied, between the universities, you know, we have some commercial entities with the gravimeter team, and then, you know, some native NASA instruments that make up the team. It makes it a really diverse group with different specialties that really add to the group dynamic of the team, which I'm sure you've experienced, Maggie.
Yeah, it's really fascinating to think that the plane holds lots of different projects, and that the projects all intersect and relate to each other. And in essence, one project sort of fills in the gap for another project. That if you're running an instrument that measures the thickness of ice, and then the person across the aisle from you is running an instrument that tells the shape of the bedrock, boy, I mean, that's great. The two of you can really work together and learn a lot more than if you were just working on your own thing. So it's a pretty interesting group of people from all over the place. So next slide, please.
I just have a question before you move on to the next slide. Mike Penn wanted to know, are the geometric shapes on the map flight paths?
Yes, they are. Great question. They are flight paths. I have near the end of the slide presentation, there's an updated map that shows flight paths that we've taken so far this year. And that is, yeah, I think, Judy, I think you've just scrolled to it, so you might be able to pop that up. I don't know. But as of a few days ago, this other map that you'll see that's very similar has updated paths. But yeah, so, and it looks sort of like water. The white area of the map we'd think would be water, but in many cases it's ice or sea ice or ice shelves. So when they're measuring on the in these areas, a lot of times it is the ice that they're measuring, and the sea ice itself is maybe in chunks and icebergs, and there are some large pieces of ice shelf that we've looked at over the last few days. And so these paths are predetermined. They're chosen probably with a lot of care before the project, and they all have different names. And so saying we're going to do the Hull Land 2 today. And so these are predetermined paths that are in some cases repeats from previous years, so that they're able to see exactly within just a few meters exactly where they flew last year and the year before, so that you're seeing change year to year in exactly the same place, which is fascinating. And in other times, they're high priority flights because they're new. There may be a new transect that we haven't flown before. So yeah, so that's a great question. Thanks for that. I think we're ready to go back to the big blue slide of the DC-8. Yeah, there we go. So it's a beautiful plane, and someone who's never really appreciated planes that much before in my life, it's a really great instrument for us, a great tool. And you can see on that those big beefy engines, and then some things sort of in the underbelly that look a little bit different than you might expect from a regular plane, and those are the instruments peeking through. Next slide, please. So again, this picture just shows some of the places in the left diagram of Antarctica over the years from 2009 to 2015, showing how many different campaigns there have been, and how much data was collected in each campaign would be interesting to know, because I know every time we come in, there's a data report that all the instrument people share, and it's like so much data, and they'll say, yeah, we got this many gigabytes of data, and it's just massive amounts. Next slide, please.
Maggie, we have one question in from Hillary Brown, and she's wondering, have you seen the southern aurora yet?
No, I have not, and I don't know exactly if I would. I don't know, John. What would I expect to see at this time of year?
Actually, the latitude that you're at is a little bit too far north to get it, unless it's really strong and you're really far out of town, unfortunately. And then down here in McMurdo, you'd think it would be unbelievable, but unfortunately the sun is up 24 hours a day down here, so we have no darkness to view them either.
Yeah, that makes sense. Yeah. So maybe someday. All right. Well, so this next slide, I'm going to bring my little pointer in, I think, if I can. Starting off with, well, I guess I can't. Yeah, in this diagram, you can see that there's a bunch of different red and blue little wiggles going down from the plane. And basically, yes, oh, thank you. What this is supposed to explain is that some of the instruments are able to use to get the topography of the surface. And so they'll send down like a LiDAR beam would bounce off the surface and go back up to the plane and give you the height of the ice. And then some of the deeper penetrating radars can go down through the ice itself. And then, yeah, so that the greenish line would be showing the LiDAR of the being able to bounce right off the surface. So it's pretty cool. And then notice down below that there's ocean, and underneath the ice shelf, there's some ocean. And this is an interesting point because, and especially in this diagram showing that sort of the orange higher bump of the land, that you have great potential for a lot of really rapid ice melt in this kind of scenario. So going to places where we think we see, yes, thank you, a high bump of the land with water below the ice, this is an area of probably great interest to the scientists. So picking those spots, we're able to use the instrument data to tell us where to go. So pretty cool. Next slide, please.
Maggie, we have another question from Leah, and she wants to know, her classroom wants to know how cold it is where you are flying.
Right. Well, it varies quite a bit. We've had pretty warm weather here in Punta Arenas. It is spring, and even though we're at the very end of the end of the Earth, um, the as far as South America goes, it's still, as John said, really not all that far south. So it's relatively nice. I mean, I have a jacket on and a hat some days, but it's not super cold. So maybe in the 50s, 40s, 50s here. But when we're flying over the ocean and going south towards Antarctica, it gets to be pretty cold. By the time we're over the continent, it's probably, below, probably 10 below, 20 below zero. And we did fly all the way to South Pole the other day. I don't know if you saw this in my journal, but check it out. It's pretty cool. It's really cool, actually. The temperature there was, I'm thinking -30. I don't know, John, if you want to jump in on this and give me a thumbs up or on my temperatures, because it's I know really really cold in the atmosphere above where we are flying, but at South Pole it's pretty cold as well.
Yeah, it's a pretty harsh environment, and I know this year, like you were saying, we can get air temperatures up where we're flying in the -50 to -60 range, which is really cold. And I just pulled up the current weather here in McMurdo right now. We're at -2 degrees Fahrenheit, so it's pretty chilly down here on the continent, but we're experiencing some really cloud-free, beautiful skies, so it's really nice.
Yeah.
Okay.
Yeah, the South
And
Pole,
we have
we all got,
two more.
I just wanted to say that we can tell in the plane when it's really cold outside, because the area where you would normally store your bags, or where you see the guys throwing the bags in underneath your seats, when you're waiting for the plane to take off, that area has instruments. And some of those instruments got incredibly cold when we were flying over South Pole. And one of the scientists went down to check on his instrument and touched a piece of metal and actually got a spot of frostbite on his hand because the metal was so cold. So it's pretty intense down there. You wouldn't want to get locked down there, you know what I'm saying? So, all right, next slide, please.
Okay, we have one more set of questions actually from Mike Penn, which relates to your slide. What altitude do you typically fly at for optimal results? And does it vary by the measurements that you desire or the instruments that you are using?
Great question. When we're commuting to Antarctica, we're flying just like we normally would at 35,000 feet or so. When we get to our target area, we descend to about 1,500 feet. So we're flying very low. I know that the threshold, some of the instruments don't like, or I don't know, maybe they operate best above 1,200. So we try and stay above 1,200 feet. And below, I can't remember, 17 or 1,800 feet. So there's sort of a wiggle room in there. The other day, we did fly at 700 feet, though, which was incredibly thrilling. And we did that mostly because we had some low cloud cover. And so we needed to fly below the clouds in order for the instruments to collect their data. And so our flight level was much lower than it would normally be. And that was a lot of fun. So we can move on to the next slide when you're ready. Thanks. All right, so one of the main tools is the ATM, and this is a airborne topographic mapper. So you can imagine that since we're trying to collect data on the surface as well as below, we need to know exactly where we are and collect really, really good data on that surface, and so that the data collected below the surface matches up perfectly. So this is a really big tool for us. The picture that you're seeing is sort of more of a Greenland view, in that there are a lot of glaciers and valleys that the smaller aircraft can fly up. In our case, we're going to be over larger sheets, but there have been a few times where we've been studying a glacier and since I'm not in the front of the plane, I'm not looking out forward, I'm sort of looking out the sides, and we'll get really close to a mountain range, and then the plane will, bank sharply up. It's really cool. So we're suddenly like, whoa, okay, well, there's a mountain range. So next slide, please. All right, so John, I'm probably going to ask you to explain this image to the folks, because this is pretty cool image. There's probably a lot to talk about.
Yeah, so on the left-hand side of the screen, that's our old sensor, which was called a KT19 pyrometer. You see it there, which gave us a very coarse resolution, or rough, not a lot of data points going across. What you're looking at there, the white is sea ice, and the dark is actually open water or lead. So you can see the temperature differences between the sea ice that has some snow on top of it, the open water, which is much warmer or red, and then the other side where we're back over to the sea ice. On the right-hand side, that's our new instrument. It's called a FLIR, which is a forward-looking infrared camera. FLIR is also just the company name that makes the cameras. And you can see a much more detailed picture. And what the scientists really like about this is that it can, I think it's letter C there, that kind of yellowish color. That's real young, thin, new ice, so probably only a day-old ice that's just formed. And understanding those the properties between the ice, or the new ice, and then the open water, we really need to understand that to get a better overall picture of how the ice surface is interacting with the atmosphere above it. And this ties into a much larger regional for global or regional temperatures and local temperatures. So it's really exciting that we have this instrument on. It's only the second deployment that's flown on, so we're expecting a lot more data coming from this in the near future.
Cool, great. Next slide, please. I already talked a little about the gravimeter. So you can see the picture on the right, how it looks just sort of like a can or something sitting on the floor. Well, it's like $1 million instrument, so we try not to kick it too much. Yeah. No, yeah, like never even touch it. And then the imagery shown just to the left of it are some of the kinds of diagrams that we can see from the data, which is pretty amazing. I'm a big fan of this instrument. I think it's really cool. It's a great idea, a great, really cool way to try and figure out whether there's bedrock close by, if there are peaks and mountains underneath the ice. Very neat. And Mike, I think you may have asked about this in a journal question. I'm thinking that may have been you that was asking about, does it actually map? And it does. So next slide, please. So yeah, and in fact, the image that I want to draw your attention to most on this is the one that's in the bottom right quadrant of the slide. Yeah, that shows that bedrock profile, and that would be something that would be really good to know. And basically, if you think about the question that oftentimes scientists are grappling with, is like, how much ice is there? And if it all melted, how much would sea level rise? And I think we think of that question, and it comes to our minds, and I know my students, it definitely was on your minds. Well, the only way to really know how much ice there is to know what the profile of the bedrock below is and how thick the ice is. So with this kind of information, you can actually determine the mass and the volume of the ice, and determine really how, and there is a great variety of density of that ice. It's not all exactly the same density. So there's some calculations for sure that have to be run. And the mathematics in this project is absolutely stunning. So everybody keep studying math. I'm telling you, it's everywhere, and it's really cool stuff. So imagine, like, if I just gave you that profile and said, figure out how much ice is in this diagram. I mean, that would be a really cool project. Like, what would you do, and what math would you need? So it's a neat project. Next slide, please. So, and John, again, I think I'd love you to talk about these images briefly. The ghostly one on the top left shows a pre-dawn view of what the radar actually, or what the ATM would look like hitting the ice if it wasn't broad daylight most of the time. John, you want to jump in on these images?
Yeah, so you explained that the top left one pretty well. That's when we fly up in the Arctic, we transit from Alaska back to Greenland, and in order to make it in time before the airfield closes, we have to leave Alaska very early in the morning. So it's one of the rare flights that we do in the dark. which gave us the opportunity to actually see the laser that's coming out of the belly of the plane on the ice surface. So that's the circle, yep, exactly what you're seeing there by your pointer. And then the two images on the right, those are the actual process data. So once the instrument collects the surface elevation points, it goes through a lot of post-processing, a lot of heavy computing, which people at Wallops, this is for the ATM instrument, actually monitor to put together these stunning 3D images that you'll see there on the right. So what you're looking at there is basically the surface of the ice, and the top right one actually has an overlay of both a digital photo, sort of what you would see, and then the laser data on the right next to it. So some pretty impressive data sets that come out of these instruments.
Great, thank you, John. The next two slides are sort of an A and a B, so if we can move to the next slide, and we'll just look at, and again, John, I'd love you to jump in on these, because this is talking about the minimum of ice in the northern and southern polar regions, and then the second slide is maximum. John, can you weigh in on this for us?
Yeah, so this is the basically current state of the Arctic and Antarctic, and the blues are bad. That's basically less ice than we've experienced over kind of all of the time that we've been taking observations. And a lot of this comes from satellite data. So satellites have only been up since the early 70s, so that's about what we have the data that goes back to come up with these changes. And again, you can see a much different ice cover in the Arctic than we've ever really experienced before from satellite observations. In the Antarctic, you can actually see some reds, which is interesting. So you might hear some folks saying that, the ice is growing around Antarctica, so global warming has ceased. There's a couple different theories as to why this ice is actually growing. And what we're talking about here, again, is sea ice. This is not land ice that we're talking about. So this is actually frozen ocean. And a lot of those reds, they think, are contributed to the wind patterns changing, actually due to temperatures changing in other latitudes around the world. So the winds are actually getting stronger and blowing away from the continent. And as those winds blow, they're actually pushing the sea ice out further away into places that it hadn't been before. So kind of a really complex picture as to why the ice is growing or shrinking in certain places, and depending on which pole you're looking at.
Yeah, and another thing that I was talking to a sea ice scientist yesterday about was, as the grounding line of the ice shelves and glaciers come farther and farther out into the ocean, that isn't necessarily that the ice is getting larger or thicker or more extensive. It may mean that it's flowing away from the continent and more quickly. So it's sort of an interesting thing to think, like, how different the polar regions are from each other, and how more ice in certain places may not mean the same thing in both places. So it's kind of a puzzle. So next slide, please. And this is, I believe, my last one, and it just echoes the differences again, showing that in the Antarctic, which is the red line, what we're seeing as far as sea ice extent is increasing, and that being, again, like the ice shelves and sea ice that are coming out away from the continent, and that the ice cover in the Arctic is shrinking, the blue line. So next slide, please. Okay, so John, this would be a great one for you. You want to grab this one? No? Okay, so we could go on to the
sorry, I missed the question. I missed the question in the chat box. What was it again?
Oh, okay. Yeah, what was the question?
The question, yeah, okay. The question was from Mike Penn, and he asked, does the air below the aircraft have to be exceptionally clear for the laser to traverse the distance without atmospheric interference? And while you're thinking about that, Maggie would like you to explain this slide afterwards.
Oh, okay. Sorry. So yeah, great question about the basically you're asking about the cloud conditions, and we definitely want a cloud-free environment between the plane and the surface. However, depending on the instrument, you can actually, ideally, you're cloud-free below. However, if you go into an area of clouds where, say, the gravimeter is the main instrument or the radar is the main instrument that we're really trying to collect the data from, those can actually see through clouds, so clouds don't necessarily affect them. However, for the laser, which is, again, one of our primary instruments, you definitely need cloud-free conditions, which makes it a challenge because trying to find a cloud-free area around Antarctica or Greenland or Alaska is pretty tough. So fortunately, we get to fly really low, about 1,500 feet, so below most of the clouds. But again, trying to determine the areas of clear air is a challenge.
John, can everybody else hear me?
Well, okay, that's okay. I think this slide here, why is the Antarctic ice increasing? We've kind of covered already, so maybe we can skip past it and go to the next one.
Maggie, are you still there?
Yeah, I'm here. Can you hear me? I think we may have. Yeah. So let me just chat for a minute about what it's like to be on this aircraft, because it's kind of fun, and I think some of the students might be curious. We have like first class seats. We're not all packed in like you would be on a commercial flight, but instead of having somebody next to you or somebody right in front of you, you have instruments and computers. So it's really different. There's all these metal racks with computers and instruments on there. You can also walk right into the cockpit. Well, you have to ask permission, but the door is open, which you'd never see anymore. And they invite you in, and I got to land in the jump seat the first day. That was pretty awesome. And there's a little galley. The middle picture shows two people about to warm up some food. So we bring our own food and we pop it in the microwave to warm it. And then the bottom right picture is down in the cargo hold. There are some instruments down there. So it's kind of neat to go down and see what's going on, blinking lights and stuff like that. There's also some special rules. We have seat belts that have over the shoulder as well as around the waist for turbulence. And if we were to take a picture with a flash, they would want to know so that they wouldn't think that there was some electrical system arcing. So we'd have to get on our headsets, which we wear all the time, and say, sorry, I just took a picture with a flash, so that people wouldn't be alerted to that bright light. So we always are on our headsets that are noise canceling, which is good because it's very loud in the plane. And it also has a microphone, so you can talk to each other and ask questions and such. Next slide, please. All right, and so again, I'm super fortunate to get to be here and to see some of this country, to see this continent, to see the beauty of the ice is absolutely phenomenal. I never in my wildest dreams knew how many textures and colors that I was going to see. It's just incredible. The one thing that I want to highlight is right under the word experience -Y, there's a sort of an orangey map. And every day there's the amazing John Sontag is really helpful in figuring out what the weather is going to be like and where to go. I've learned so much about weather, never knew that. I've gotten to the bottom left picture shows I was with a group of students here right where I am today on this campus at University of Magellan, giving a talk to the students who are very interested in not only learning English, but also, pursuing great things. So that's been amazing. Just being part of learning about the data collection and journaling with you guys and being able to do this talk, and so many ways that I'm doing outreach to share what I'm fortunate enough to get to learn about. So I'm living the dream, just loving every minute of it. So that's pretty much what I have to share, and I've used up a ton of time because there are so many great slides in here that John and company have put together for me to use. So I guess questions at this point would be good.
Yeah, Maggie, great presentation. Thank you, John and Maggie, for doing that and explaining the science. Very interesting. We had a question from your school earlier from Wendy, who is managing the class or two, and they wanted to know how cold it is in the airplane when you fly.
Yeah, it's actually pretty comfortable. I would say that if you're on a regular flight and you felt just a little bit chilly, it would be like that. They keep it right around 69, 70 degrees. But whenever a cargo hold opens with a scientist going down below, then the cold air from down below tends to creep up and get by your feet. So your feet are a little bit colder than any other part of you. But I have brought along a little like fleece blankie, but I haven't needed to use it yet. So I have just I have a little coat and a hat, and sometimes I'll put on my hat. But it's pretty comfortable overall. Great question. I
Yeah,
know it's
sorry.
like 11, 12 hours, 11 or 12-hour flights, so you don't want to be cold.
And I guess related to that, how cold is it outside? Like, what's the difference between the inside and the outside?
Yeah, so if we're flying at 35,000 feet, it might be minus 50 degrees out. And so if it's positive 60 inside, it's a pretty big difference. So, you can definitely, when you're on an airplane, if you feel the window, you know that it's a lot colder outside. So if we're really high, it might be minus 50 or more, or colder outside. So we keep a pretty good warmth inside for sure.
Okay, and Mike, Penn, and students need to go home, but they'll watch the archive. They said thank you, and they're enjoying it and reading your journal entries.
Great. Awesome, Mike. Thanks for coming. It's great.
There was a question earlier, and I don't know if John wants to state what the question was, but they were asking, again, from your school about seismic activity under Antarctica, and John explained it, but maybe for the archive, can you tell them what's going on with seismic activity in Antarctica, John?
Hello again. Yeah, so we're actually sitting on Ross Island, which has an active volcano on it, which is called Mount Erebus. And you can actually see a plume of steam coming from it kind of constantly. And I know there's a lot of different science teams out here that are setting up seismic arrays, basically a bunch of different seismic instruments all over the continent. So it's a pretty active, I haven't felt any tremors yet, but definitely a pretty active environment down here where we are in Antarctica.
Okay, thank you. Oops, sorry, I'm losing my chat here. There was a statement that came from Eliza Coyle, and she said, it's not a question, but in elementary school, she wanted you to know that some teacher fans stopped by to watch, and 2 first graders did push-ups on the hour with your crew. That's awesome.
That's cool. Yeah, because we try to do push-ups on the hour because there's a lot of sitting. I think how crazy it is to get on a plane, travel for 12 hours, and then get off the plane in exactly the same place you started, right? So we know we're sitting down a long time, and you get pretty stiff. So there's some people on the plane that'll come by and rally, and we'll all do push-ups or sit-ups or something like that to try and keep our muscles from getting too sore. So good. I'm glad some other kids are doing them with us. That's really awesome.
That is really fun. I love it. And
I see the question about wildlife.
I
can jump in on the wildlife. We try really hard to stay away from wildlife. So if there are colonies, they're mapped ahead of time so that we know where our flight plan needs to go. So we try to avoid them because part of Antarctica and part of the Antarctic Treaty really is to preserve the continent for science and to keep it, the way it is. So we don't want to disturb large colonies of penguins, for instance. Although of course we want to see them because they're amazingly cute and cool, we try not to get in their way. So we move away from them. But we have seen a small bunch of penguins that were there, and they got a little freaked out by our plane. It was when we were flying low. And we have seen some seals also when we're flying low. And we saw some pink flamingos the other day when we were taking off. And don't make you think that it's like super, super warm, but they are. Like I looked it up because I thought, wow, I didn't know flamingos were down here, but they are. So it's normal to have them down here. Pink flamingos, yeah. So those are some of the cooler animals that we've seen. And I thought there was something about microbial, yeah, from Lauren, 6th grade, about microbial activity in the ice. It's a great question, and I would love to get back to you on that when I can talk to some scientists on board that may know more about that than I do. So Everett, gold star, nice question.
All right, so I think you kind of caught up also with the questions that we had. So Wendy actually now has a new question. In order for the gravimeter to determine underlying matter, rock, ice, and water, does it need to factor out the effect of elevation, higher elevation having more mass than under the surface? Can you give a sense of the complexity of the algorithms involved in making these calculations? Whew. All right.
Yeah, nice one. And if John wants to jump in too, he's welcome. I don't know if his connection's gone or not, but this instrument is incredibly precise and can make really micro measurements. I know that, and that the elevation would probably play in a little bit. And I asked sort of a similar question about, does different rock type, is that going to affect the readings too? And basically the mass of rock is so much greater than either of the things that you're raising, whoever is asking this awesome question, Wendy's question, or the type of minerals in the rocks, that those are much sort of smaller differences than the kind of the mass that we're looking for. But, you know, I'm sure that it's a very precisely designed machine, and I would imagine that there's lots of things taken into account with it, yeah. And I don't know if John is available to jump in at all.
Yeah, Maggie, you did a great job. I couldn't have done it better myself. And I think just one other thing to point out about this instrument, of how sensitive it is, like you said, this is one of those instruments that causes a big logistics headache of being powered on 24 hours. So it needs such high calibration that it needs a constant power supply. So even when we're on the ground, we have to make sure that this is powered at all times. So it's a very precise instrument.
Cool. So I think somebody has to stay with it all the time too, to make sure that the power doesn't disappear. So someone has to like babysit it at night. So yeah.
Wow. Interesting. Okay. So Judy's asking.
Ooh, I love this question.
All these instruments. Yeah.
Well, I love this question because it's one of the things that I've learned on this adventure, is that different departments that are asking different questions will design and build their instruments. There are exceptions, but for instance, this one little tool that wasn't really mentioned in this presentation because it's on board as a test flight right now, it's called the Mini-Rad, and it's designed by Dr. David Gallagher at University of Colorado Boulder, right around the corner, guys. And he's a research scientist at CU, and he and his team have been asking questions about microwaves. And so he's designing an instrument that the previous instrument he had designed was like this big 300-pound behemoth, and it was really difficult to fit on a plane, let alone, you know, carry properly. And so he's redesigned something in the last couple of years that it's now 2 pounds. It's about the size of a lunchbox, and it's mounted in the belly of the plane. Right now it's really tiny. And so all of that was happening, and he told me the story about how he was about to get on the plane to get to Punta Arenas, and he was asking his design team, which are grad students, some professors, some postdocs, and saying, guys, I have to have this instrument. I'm getting on a plane in a few hours. Come on, I've got to get this instrument. They pulled 2 all-nighters designing and building this instrument and getting everything ready, that they were so tired that they wrote on the instrument the fore and aft, which were designed to be like the front side of it, the back side of it. They wrote on in Sharpie, and they put it in the wrong way. So when he tried to mount this thing into the plane, it wouldn't fit, and he didn't have the right size bolts and stuff because his team was so tired from designing and building the instrument. So in a lot of cases, study engineering, because you get to design these cool instruments and then maybe even go and be with them. Some of the engineers that designed them are on board because they're the ones that know the most about the instrument. So There's just so many great engineering, science, and math applications in this project. I'm just bursting with it, and I just want everyone to keep studying math and science.
Yes, excellent example there, Maggie. And how integrated they all are. So let's see. I don't know if there's any other questions. I think we're okay. So if you do have additional questions for Maggie and the team, we would like you to post them on her journal, and then she can respond to them. And we also want to take a moment here and thank John for joining us all the way from McMurdo, Antarctica. We're glad you were there since Nathan was unable to join us today. Like I said at the beginning, this event is being archived and recorded, so we'll share it on the website through the journal, as well as send it out to everybody that registered. And if you can, before you sign off today, please click on our poll and let us know how you like this event. In the meantime, I'm going to stop the recording, and if you would like to say goodbye or hello or whatever, you're welcome to do so. But let me turn it over to Maggie and John to say goodbye, and thanks again for joining.
Yeah, well, thanks you guys for making time in your day to come out. John, you want to say any parting remarks?
Yeah, thank you, Maggie. You're doing a great job, and thank you, PolarTREC. It's a really great program, and really glad to have all the classrooms online participating as well.
Yeah, it's really awesome. It's great to communicate with you all. There are other ways to connect. We have this thing called XChat through NASA that allows classrooms to jump on and ask questions, kind of more like texting. It's pretty cool, and you can ask questions of the scientists as we're flying. So Wendy, you could send me a text or an email if you want that information. Also, I saw there was a couple other questions, like Marianne, you were asking about wildlife, and we can talk more about that. But also check out my journals, because there's a place for you to leave me questions and comments. In fact, I think I made an assignment for you to do that. And I've gotten a couple of great questions from students already. I'm loving answering them. So go ahead and throw more questions at me, because I'm here to connect with you and to share this with you. So use it.
Yeah, you did a great job, Maggie.
All right.